we have iron 2 plus and iron 3 plus. One of these we call iron 2, the other we call iron 3. And iron 2 goes by the old name, ferrous. And iron 3 goes by the old name ferric. So ferrous and ferric. Cobalt's the same. Some of these others. So there's select ions that appeared on the list. And then we continue on, and then we hit some more fixed charged ions. What are some other fixed charged ions? The first ones we're going to hit as we go across. All these are variable charge until we get to copper is variable charge. Copper is +1, +2. Cuprous and cupric. Well, if you haven't started memorizing these, then it's a good thing to get started memorizing some. It's not all of them, just some. Take a look at your supplement. Those are the ones. Zinc, cadmium, and silver. Zinc, cadmium, and silver are always a fixed charge. And so we go on, and then we hit zinc. Zinc always has a charge of. Is a charge on zinc. +2. That's correct. Was there something that clued you into +2? Take a look. Do you see this 2B? And so look at this is 2A. That's 2B. This 2A, what's the charge on 2A? +2. And so on the 2B, what's the charge? +2. So zinc is +2, and then cadmium is also +2. And so those are fixed charge. So these are going to be fixed at. So zinc ion. And cadmium. No Roman numerals needed here because there's only one charge. And so if you have zinc ion, it's always 2+, or cadmium ion, it's always 2+. There's one more that's always fixed charge. Which one is it? It's silver. You know the charge on silver? Silver is always +1. Yeah. So we just say plus. So this is the silver ion, Ag. These are fixed. And so this is like a little island of ions, because if you look, this is the sea of variable charge ions. Once you ever pass scanning and yttrium, it's a sea of variable charge. And then there's a little island of fixed charge species here. The variable charge creeps into this. This is called the main group here. This last 6 columns here, the first 2 columns, these are the main group. And so the variable charge creeps over here. So for example, lead, do you know the common charges on lead? +2 and +4. Tins, same thing, +2 and +4. So these are variable charge. As you get into the upper part, let's say we divide it, these are going to be variable charge down here. Up here is more fixed charge. So aluminum's fixed charge. What's the charge on aluminum? Aluminum's always +3. And so the variable charge creeps over here. This is going to be fixed. And that will be aluminum. And so one way is that you have the sea of variable charged ions. We always need a Roman numeral. Those are going to creep down here. But once we get on the upper part here, it becomes fixed. So for example, aluminum is always 3+. Now it gets tricky with some of these other elements here. Like, we know fluorine. Let's go over here. Fluorine is what? Fluorine's -1. But we don't call it fluorine -1 or fluorine ion, we call it fluoride. that's fixed charge. Chloride is fixed charge. What else? Well, oxygen. Oxygen forms a fixed charge ion. What's the charge on oxygen? Yeah, -2 or 2 minus. And do you know what we call it? We call it oxide. It's fixed charge. S2 minus right below it is fixed charged. We would call this sulfide. Well, what else do we have? Yeah, nitrogen, which would form. And what's the charge? 3 minus, and that would form nitride. Below that, we would have phosphide, E3 minus. And so do you see a pattern with the charges? And the pattern with the charges goes like this. You know, if I have lithium, lithium is 3 electrons. If I lose 1 electron, then it has 2 electrons. So it stops here, it's fixed charge. So it'd have the same number of electrons as helium. If I have sodium, which has 11 electrons, and it loses 1, then it's going to end up having the same number as neon. Magnesium has 12 electrons. If it loses 2 of those, it forms magnesium 2+, which would have the same number as neon. Yttrium with 3+ is 39 electrons, so if it loses 1, it's 38. If it loses 2, it has 37. If it loses 3 electrons, then it would be like krypton. But the same thing, bromine has 35 electrons. If it gains 1, it forms bromide with 36 electrons, so it would be like krypton here. And so we see the pattern. The pattern is we're trying to get the same number of electrons as in noble gas, the nearest noble gas. And so fluorine gains 1, it has 9, gains 1 to go 10. Oxygen is 8, gains 2, goes to 10. Nitrogen has 7, gains 3, goes to 10. What about carbon? Carbon is carbon's in an interesting position because carbon is halfway between helium and neon. So if carbon gains 4, it's like neon, or if carbon loses 4, it's like helium. And so carbon, you know, we can have this. We can have carbon with a +4 charge. Let me put that in quotations, or carbon with a -4 charge, or 4 minus charge. Carbon with a -4 charge is called carbide. And carbon with a +4 charge, this would just be carbon, and sometimes we put a Roman numeral 4 because it doesn't occur as a lone ion. You know, when we see carbon with a +4 state, it's because it's combined with something. So for example here, if we look at CO2, you know, carbon dioxide, what is the charge on oxide? Well, the charge on oxide is -2. We have 2 oxides there. So if we have 2 oxides, what's the charge on carbon? It's got to be +4, right? That way things balance out. And so this is carbon in the +4, but sometimes it's hard to lose all 4. So for example, in carbon monoxide, you know, oxide's -2, then carbon must be +2. And so here we start to see variable charge occur, but we don't use this Roman numeral system. So for example, carbon dioxide, they don't call it carbon Roman numeral 4 dioxide or carbon Roman numeral 4 oxide. They just call it carbon dioxide. That's it. All right, let's continue reviewing the ions. These are what we call monatomic ions. These are monatomic ions. like the anions end in I, the cations just are the regular name. And then we'd like to know the eights, the polyatomic eights. And look at the eights. We can start off with carbon. Actually, we don't start off with carbon. You know where we start? We start off with boron. Why do we start with boron? Because if you memorize boron, you can figure out the rest. And so, when you memorize boron, what is borate? What's the formula for borate? Yeah, BO3 charge? 3 minus. What group number is boron in? 3A or 13, so it's easy to remember. 3, 3, 3, 3. And then we have what's next to boron? Carbon. What's carbonate? CO3. And the charge? Or is it in your notes? Did you copy the table off the board last time? What is it? 2 minus. 2 minus. It's carbonate. And then, what else? Nitrate. What's the formula for nitrate? NO3. NO3. Charge? -1. Yeah, so if we memorize borate, we could figure out the rest. Not only can we figure out the rest of the eights on the periodic table, there are some eights we can't. Just the periodic table-based eights. We could also figure out the ites. What's the difference between an 8 and an ite? ITE. One less oxygen. And so if I know this is nitrate, then nitrite's easy. What is nitrite? NO2 minus. We could also figure out a whole bunch of others. The others are tricky because not everything forms, like for example, carbonate does not necessarily form a carbonite. If a carbonite did form, it would be CO2, 2 minus, right? But there is no carbonite ion. And so just for some of these, we're going to have other examples. Borate, that's pretty much it. Now, we go nitrogen to oxygen to chlorine, or fluorine. Actually, let's go to fluorine here. So what is fluorate? FO 3 minus. This is fluorate. Okay, if this is fluorate, well, fluorine happens to form the whole series. So let's take a look. Fluorine, chlorine, and these species do. So if this is fluorate, what is fluorite? So from this, we can get fluorite. Fluorite is 1 less oxygen, so it's going to be FO2 minus. And then we have something called hypo. Hypo means 1 less oxygen. And so hypofluorite would be FO minus. I guess we could do hypofluorate, but if we did hypofluorate, what would that be? Hypofluorate would be the same thing as fluorite. so we wouldn't do hypofluorate because there's already fluoride. But there's one other thing, we could do per. Do you know what per means? Per means one more oxygen. So if we did per hypofluorite, then we're at fluorite, so no reason to have two names for the same thing. If we did per fluorite, we'd be at fluorate. And so again, that's not necessary. However, if we did per fluorate, then there's nothing. So per fluorate would have one more oxygen than fluorate. And so it would be FO4 minus. And so by memorizing borate, you know, you can derive a lot of ions from that. And so it cuts down on the memorization. But you'll have to know the pattern. All right, so chlorine is below fluorine. Chlorate would be ClO3 minus, and the same thing. For chlorate, there's perchlorate, chlorate, chlorite, hypochlorite. Same kind of series. We don't see the whole series for nitrate. No. Or carbonate or borate. All right, below carbon is silicon. Actually, below boron is aluminum. And so I know what borate is, right? I asked you to memorize borate. What is aluminate? I didn't ask you to start here. I asked you to memorize boron, and I asked you to memorize silicon, because those are two easy ones to remember. And so silicate is what? SiO4 in the charge? Yeah, SiO4, 4 minus. What group is it in? 4 or 14. And so it's easy to remember, 4, 4, right? SiO4, 4 minus. Easier to remember. So silicate, and then what comes next after silicate? Phosphate. What's the formula for phosphate? PO4, 3 minus. After phosphate comes sulfate. Sulfate is SO4 charge, 2 negative. And so from silicate, we can derive a whole bunch of others. So, for example, sulfate, we also have, you know, sulfite. What is sulfite? SO3 charge, 2 minus. So we don't have to memorize it. We know. 1 less oxygen, same charge. That's sulfite. We also can derive other ones like thiosulfate. Thiosulfate. Thio means replace oxygen with sulfur. And so thiosulfate, anybody recall the charge on it and what the composition is? So what we do is we'll take sulfate, remove an oxygen. So that leaves us with how many oxygens? 3. And then add a sulfur, and that gives us S2O3, 2 minus. That's thiosulfate. So you don't really have to memorize it, you know, by flashcards or whatever else.
I'm sorry, this says hyposulfate?
Thio, T-H-I-O, thio. T-H-I-O. We have others like selenate. What do you think selenate is? You know, selenium is below sulfur, and so selenate, what would you guess selenate to be? What? SeO4 in the charge? It's right below sulfur. Yeah. So this one's going to be too negative. How about this one? What do you think illuminate is? Maybe I should have had you guys memorize from the beginning. Rather than start off at silicate, I should have started off at illuminate. Well, what do you think the formula for illuminate is? ALO4? ALO4 charge? No, aluminum ion's 3+, but illuminate's not.
Oh, plus 3.
No. Sometimes you could use the pattern to see it. What would the pattern say? Do you see it? It's ALO4 charge? 5 minus, yeah. ALO4 5 minus. So do you see it goes 5, 4, 3, 2? See the pattern? Now, why didn't I ask you to memorize illuminate? The reason I didn't ask you to memorize illuminate is because it's easier to do silicate. Because it's a 4-4 in group number. It's 4-4 in group number 4. Borate is a 3-3 in group number 3, so it's easy to remember. Otherwise, you should start off with illuminate.
How does that follow the pattern? -1.
How does it follow the pattern?
Yeah.
The pattern is 2, 3, 4. Next one to the left, it should be 5. So 2, 3, 4, 5. Obviously, there's a connection to structure here. If we knew more about the structure, you know, how everything's arranged and internal structure, this kind of stuff, it's a lot easier to predict. You know. But right now, we're just looking for patterns that we can recognize, and that'll help us remember certain things. Okay, so let's illuminate. And then, of course, there are others that that are just straight memorization, you know. And so, all these ions I can figure out just based on periodic table. You know, just memorize a couple. I'd memorize probably a borate and silicate, and the rest I could figure out, all of them. But there are others that you just have to memorize. You know, things like chromate, dichromate, manganate. Well, actually, manganate's not that common. Permanganate is much more common. Peroxide, et cetera, et cetera. So there are a whole bunch of others, you know, that you just memorize. Acetate, oxalate, et cetera. Others to memorize. right, so when we name compounds, we just put the cation name followed by the anion name. So let's get some practice. But we'll probably back up a little bit and then take a look. Some of the homework problems here. All right, write the chemical formula of each of the following. And then probably we'll name them too. You can't see, I don't know why the color is not working on this camera. This is black and white. The white ones are fluorine, the black ones are chlorine. And so A is two fluorines bonded together. What's the formula for that molecule? Molecule would just be F2. You know, that would be a diatomic element. That would be just fluorine. Elemental fluorine, F2. B, we have a chlorine bonded to a fluorine. So it would be like this. Chlorine bonded to a fluorine. B, that's a diatomic compound. It's a compound because it's two or more elements, so there are two different elements here. It's diatomic, it's two atoms. And it's a compound made up of non-metals, so it's what we call a molecular compound. The rules for naming molecular compounds are we use the prefixes. So this would be called chlorine monofluoride. Chlorine monofluoride. What would C be? That would be chlorine with how many fluorides? 3. So we call it chlorine trifluoride. Chlorine trifluoride. D.
Chlorine tetrafluoride.
Tetra is 4, but this one actually has 5. So what's after tetra? Penta. So the last one would be fluorine pentafluoride, or not fluorine, chlorine pentafluoride. So ClF5 is chlorine pentafluoride. Yeah. Okay, let's take a look at number 4. Write the chemical formula of each of the following. A compound made up of a crystal with 2 particles coming from chromium atoms and for every 3 particles coming from oxygen atoms. And so it's a crystal. Crystals form a lattice structure. And so we have 2 chromiums and 3 oxygens in this lattice. And that's a ratio. And so here would be a chromium. And then we'd have an oxygen, and then a chromium, an oxygen, and another oxygen. So this gives us 3 oxygens to every 2 chromiums here. Since it is a lattice structure, it extends off in 3 dimensions. So it just doesn't stop here. It continues. And so we could build up this lattice in 3 dimensions. We just add more atoms in here. So it would go in all directions because when we have a lattice structure, is there a distinct end? No. I mean, it can continue on. You could just grow bigger and bigger crystals. You know, how big of a crystal can you grow? Well, people are trying to always grow bigger crystals. There's no distinct end. You know, this is the biggest crystal you can grow. Crystals can grow quite large. And so something like this, since there's no distinct end, then we can just keep adding more and more ions to it. And so when we do a formula for something like this, we do the simplest whole number ratio. And the simplest whole number ratio is 2 chromiums for every 3 oxygens. And this is called the empirical formula. The empirical formula is the simplest whole number ratio. That's because this thing can go on and on. I mean, there could be a huge number of chromiums and a huge number of oxygens there. But we have to name this. And so how should I name this? Should I call this dichromium trifluoride? Dichromium trifluoride. Does that look right to you? No. We wouldn't call it dichromium trifluoride because this naming system is reserved for molecular compounds or compounds made up of nonmetals. This is what we call an ionic compound. I can tell it's an ionic compound because we have a metal with a nonmetal. So metals and nonmetals make ionic compounds. And so we just have to name it according to the ions. So what's present as far as ions go? What's present is this. I'm going to have 2 chromium ions and 3 oxide ions. Now the oxide, that's not so difficult because I know the charge on oxide. The charge on oxide is always 2 minus. But I don't know the charge on chromium because chromium can be 2 plus or 3 plus. Those are the 2 charges on chromium. So is this chromium 2 plus or is this 3 plus? The way we can figure it out is by looking at the net charge. This is going to form a net minus 6 charge. Over here, this has got to be plus 6. The charges have to balance. In order for this to become plus 6, it cannot be plus 2. Because if I have 2 of them at plus 2 gives me plus 4. I need 2 of them at plus 3, which gives me plus 6. And now it's balanced out. And so what we call this is chromium. It can be chromium 2 or 3. This is chromium 3 oxide. Now we don't say trioxide. The reason we don't say trioxide is because we can figure out how many oxides we need just by balancing the charge. So this will result in 2 chromiums and 3 oxides. Chromium 3 oxide. Okay, B, the compound made up of a crystal with 1 particle coming from barium for every 2 particles coming from chlorine atoms. So what we have here is we have Ba Cl2. Now, do we have this problem? For example, barium. Is barium variable charge or fixed charge? Take a look at the periodic table and see, is it in the variable charge region or the fixed charge region? I'll post the periodic table here. See, barium's down here. Fixed charge or variable charge? This fixed charge, what is the charge? So we don't have to write the Roman numeral. So we just call this barium. We don't need the Roman numeral 2 because there's only 1 charge. So it's just barium, or barium ion. The same thing with chlorine. What's the charge on chlorine? minus 1. So this is why we have two of them. We need two negative charges to balance out the positive 2. And so the name for this is just called barium chloride. It's not called barium dichloride because, again, we could figure out that we need two chlorines for every barium based on the charges given.
Okay, what's next? I guess that was B, now we're on to C. Compound made up of molecules with 12 carbon, 22 hydrogen, and 11 oxygen. So this is 12 carbon, 22 hydrogen, and 11 oxygen. Can we name this? Do you know the prefix for 12? You know, decadi or something like that? But you know what? This is not a binary compound. Binary, we would use that rule. And so binary would be if we only had 2, but we have 3. And so the rules are much more complicated. And so something like this goes by its common name. This is sucrose, or just table sugar. There are a lot of different kinds of sugar: fructose, glucose. This one's sucrose. The compound made up. So this one you would just have to have memorized or look it up. The compound made up of molecules with 3 hydrogens, 1 phosphorus, and 4 oxygens. Okay, do you recognize PO4? What's PO4? PO4 is phosphate. What is phosphate? PO4? 3 minus. So this is phosphate. And then how many hydrogens do we have? We have 3 hydrogens. That makes sense because if this is 3 minus, we need these 3 positive hydrogens to balance out the charge. And so what do we call this? We call these hydrogen ions, or hydrogen. Hydrogen. And this is phosphate, so the name of this is hydrogen phosphate. Hydrogen phosphate. There's another name for hydrogen phosphate, or it's called phosphoric acid. We'll talk about naming acids in a little bit. That'll be it. Okay, number 6, write the formulas of all elements that exist as diatomic molecules under normal circumstances. So we're going to do number 6, number 8, number 10. And so let's take a look at those. Also number 12. And why don't you work on those and I'll be right back.
So number 6, what are the formulas of all elements that exist as diatomic molecules under normal conditions? Uh-huh. Hydrogen, oxygen, iodine, fluorine. Boron? Boron doesn't exist as, solely as diatomic. It can form diatomics, but it doesn't really exist as diatomics. Bromine? Yeah. Bromine, yeah. That's. So there's 7 of them. Was that 7? So we had hydrogen, oxygen, fluorine, bromine, iodine. Carbon is not. Carbon is going to form graphite or diamond. Chlorine, yeah. Nitrogen. Nitrogen does. So those would be it. Number 8. Given names, write formulas. Given formulas, write names. Germanium. That's just the symbol. What is the symbol for germanium? Ge. Fluorine. F. Well, should we call it F or F2? Fluorine's one of those diatomics. So should we call it F or F2? It's ambiguous. I don't know. Sometimes if they're talking about fluorine element, then F2. If they're talking about fluorine bonded to something, then they're talking about fluorine atoms bonded to something, not F2 gas. And so it's a little bit ambiguous. So it's either F or F2. Usually they're talking about F2 because if these are the elements, then we're talking about elemental fluorine, which would be F2. Argon, Ar, gallium, Ga. That rounds it out. How about 10? O2 is oxygen. We could call it oxygen, we could call it molecular oxygen, we could call it diatomic oxygen, or we could just call it oxygen. If we just call it oxygen, then there's a little bit of confusion. Could it be O or O2? But if we said diatomic oxygen, then no problem. Or if we said molecular oxygen, no problem, because it forms molecules of O2. 10. The next one is Ca, which is calcium. Now, there's a little bit of confusion here because there's overlap in names. If I said you need calcium in your diet, am I talking about this stuff, which is called calcium metal, or am I talking about calcium ion with a 2+ charge? What am I talking about? Calcium metal or calcium ion? If you need more calcium in your diet, do you want to take the metal or do you want to take the ion? Yeah, it would be safe to take the ion. If you take the metal, you're going to be in trouble. The metal will probably end up causing severe burns in your mouth. This metal is very reactive, so the ions get. But are we talking about the metal or are we talking about the ion in this problem? We're talking about the metal. So what some people do is they'll just say calcium metal. That clears it up. Then for sure you're not talking about calcium ion, which has the 2+ charge. Next one, Ba. Barium, so that would be barium metal, and Ag would be silver metal. Here, for silver, you'd rather have silver than silver ion. Silver ion, causes problems, potentially health problems. All right, let's go on to 14, or actually, no, I guess we're on 12. Let's go on to 12. chlorine, magnesium, nitrogen, vanadium. So we need to write the formula. What's the formula for chlorine? Cl2. If it's not specified, then it's safe. You know, this is one of the diatomics. Just go ahead and write it as a diatomic, Cl2. Magnesium, Mg. Is that Mg2 plus or Mg? It's a little bit ambiguous, but if it's just standalone magnesium, then I would assume it's magnesium metal, which means it's just Mg, not Mg. To make sure that there's no confusion, they should have written magnesium ion, if they were interested in ion. But in this particular case, they're interested in element, which is just Mg. Nitrogen. N2, vanadium. V. So we have non-metal binary compounds, you know, 2-element compound. We're going to look at 14. CCl4. Carbon chloride. Chlorate. Well, we have rules. This is molecular because these are made up of nonmetals. So this is binary, molecular. So we use the prefix, like think carbon dioxide. Carbon dioxide, binary, molecular. Molecular being made up of nonmetals. And so this is binary molecular also, made up of nonmetals. We name it like, you know, that naming system. So this is called carbon, and 4 is tetra. So this is carbon tetrachloride, the liquid. So carbon tetrachloride. The next one, CBr4. This would be called carbon tetrabromide. The second element gets the I ending. This one, yeah, nitrogen oxide, except there's only one oxygen, so we call it nitrogen monoxide. Nitrogen monoxide has a common name. This molecule actually won Molecule of the Year not so long ago, I think 5 years back or so. It has another common name, which is called nitric oxide. Nitrogen monoxide or nitric oxide. The next one, dinitrogen monoxide. What's the formula for that? Dinitrogen monoxide. And so this is dinitrogen monoxide or nitrous oxide. You recall the ich-aus. Ich refers to the higher charge, aus refers to the lower charge. And so what is the charge on nitrogen here? You know, if oxygen is -2, then nitrogen is, oxygen is -2, nitrogen has to be +2 to balance out the charge. And so it looks like ich is +2. Over here, nitrogen, we have 2 of them, but if oxygen is -2, then each nitrogen must be, if oxygen is 2 minus, then each nitrogen must be +1. And so nitrous oxide. Now, the ich-aus doesn't refer to a specific charge. It just refers to a higher charge and a lower charge. So ich goes to the higher charge, the aus goes to the lower charge. But unfortunately for nitrogen, there's more charges. And so we just ran out of Al's it. Is we might have something like this, NO2. NO2 is nitrogen dioxide. And what would the charge on nitrogen be in nitrogen dioxide? The charge would be +4. I mean, we have two oxygens at -2. And that means nitrogen has to be +4 to balance things out. Now this +4, it's it's on charge, so sometimes we'll just write it as no Roman numeral like this, nitrogen 4. Because oftentimes to get that charge on nitrogen, we have to combine it with some species like this. And so what we see is nitrogen, the charge on nitrogen is variable. It depends on how much you burn it. For example, nitrogen is hard to combust. Carbon is much easier to combust. But well, when we say we have complete combustion, we just go to CO2. What would the charge on carbon be here? Yeah, well, if oxygen is -2, that gives us a -4 total net charge. And then we have only one carbon to balance it out. So this one carbon must be +4. And then it's balanced. Why do I say carbon dioxide is complete? Why isn't carbon trioxide considered complete combustion? How about carbon trioxide? Well, the problem with carbon trioxide is this. If each oxygen is -2, or 2-, then that means the carbon must be +6. If the carbon's +6, then I overshot it. Let's see. So carbon goes here, +1, +2, +3, +4. It likes to stop at +4, right? It shouldn't go beyond that. And so it's overshot it. And so carbon trioxide would say it's too much. So it'd be carbon dioxide. But it doesn't mean I always have to go to +4. For example, carbon monoxide, what would the charge be on carbon monoxide? +2. And so this is what we call partial. And so it's only went part way, not all the way to +4, but part way to +4 in its reaction. And so nitrogen can do the same thing, because nitrogen can either gain 3. If it gains 3, it forms, species with 10 electrons, and we call it N3-, which is called nitride ion. And so nitrogen can gain 3 or potentially lose how many? 1, 2, 3, 4, 5. It could lose up to 5. When I look at this, has it been completely combusted? No. Nitrous oxide can still go on to nitrogen monoxide. Nitrogen monoxide could go on to nitrogen dioxide. Now, is nitrogen dioxide complete combustion of the nitrogen? That is complete oxidation of the nitrogen. What is the charge on nitrogen here? +4. But didn't we say we could go all the way to +5? And so this would not be complete. There should be another species that takes it all the way to +5, which would represent complete reaction with oxygen. And so we can get some information from the patterns that we see here. Okay, so we have dinitrogen monoxide, then we go to sulfur dioxide. Now let's take a look at sulfur. Sulfur would like to gain how many? Would like to gain 17, 18. Would like to have 18 electrons, right? Like this. On the other hand, if sulfur lost how many? 6. Then we could get to 10. So it's either shooting for 18 or 10. But in order to lose 6, that's losing a lot of electrons here. And so sometimes that's not so easy to do. It might just go part way. And so let's take a look at this compound, sulfur dioxide here. This one's a little bit tricky because is that an oxide or one peroxide? So if we look at O2, it could be an O2 2 minus, or it could be a 2 O2 minuses. And so is it 2 oxides or 1 peroxide? Oh wait, no, did I get it right? Yeah. Peroxides are not stable, so we try to avoid these. Avoid if possible. Which leads me to think it's 2 oxides rather than 1 peroxide. Okay, if it's 2 oxides, what's sulfur then? Sulfur should be 4 plus. Over here, sulfur would be 2 plus. Balance out the chart. So avoid if possible, well, we just avoid it there. We're going to call it sulfur dioxide, SO2. Okay, let's take a look at the next one. And we'll take a break. The next one is sulfur hexafluoride. And so sulfur with how many fluorines? 6. So fluoride is, what's the charge on fluoride? -1. And so what must be the charge on sulfur? This gives us a net -6 charge. That means this has to be a net +6 charge. In other words, sulfur should be +6. Now +6 is unusually high. You know, if it were just straight +6, it'd be extremely reactive. So sometimes we show this in parentheses. This and a Roman numeral 6. Because usually it's not an ion that stands alone, it's an ion that's combined with other atoms to help stabilize it. Okay. Can we have sulfur? What's after 6? What's after 6? Hepta, right? Is sulfur heptafluoride possible? Is sulfur heptafluoride possible? No. That would mean overshooting. If we have sulfur, we stop at neon with 10 electrons. We don't go to 9 electrons, which would be fluorine. That would be it. But didn't we see a CO3? I said the same thing here. We aren't going to form CO3 either. But I thought I saw a CO3. Yes, you did see a CO3, but it was a CO3 with a 2 minus charge. The 2 minus charge helps quite a lot because carbon would be +6. But if we have 2 extra electrons, that drops carbon's charge from +6 down to +4. Is carbon +4 okay? Yeah, carbon +4 is okay. And so carbonate's okay, however carbon trioxide is not okay because it doesn't have those extra electrons. All right, I'm going to stop here, we'll take a break, and then we'll continue with the nomenclature.